Okay, so here we are just continuing this parameterized and promise streaming. As we mentioned, this is the idea. I mean, there are two ways essentially to consider big graph or big data handling. Two famous one is streaming, the other one is map reduce, or more generally, massively parallel computations. So there's a lecture on that one that on my introduction to algorithm, the last class I'm talking about it. And here I wanted, we are talking more about the streaming case. And we were talking about this parameterized streaming, a way to handle that. And we talk about this, that here there are two ideas. One is that if you have some promised streaming, in a sense that, like, let me go to the things. So here, essentially, there were two versions that we have considered. We considered a graph that is coming, the edges are coming one by one. And the idea is that, I mean, we want to have some algorithms which are sublinear, preferably in n, the number of vertices, but even in m, the number of edges is reasonable. It is called semi-streaming model. And then you can have a one-pass model or multiple paths, and also this kind of insertion only, or the case that we have the dynamic case and edges can be added or deleted. We talk about this kind of parameterized streaming, that the goal is that we want to get some algorithm with the running time, with the space which is f of k times polylog n. And this was essentially the ideas come from fixed parameter algorithm. There we want to get some running time for the algorithm, which is f of k times poly n. So here it is polylog n, and this is for a space. There essentially poly n, and that's for time. We talk about vertex cover in particular. We talk about kernelization, that kernelization is the one that we are considering a graph, and we are reducing to much smaller graph, such that if the size of the optimum solution is k, which is generally the parameter that we are talking about, then the size of this new graph G prime, which is in some sense the sketch or kernel, these are very similar to each other, the size should be f of k. And if it is f of k, then we can, I mean, and we know that what is the idea is that that if you find a solution in this reduced graph, reduced instance, here, then also it is a solution for here. So a solution here would be a solution here. And as I mentioned, this would be, I mean, if you can get this graph, which is f of k, then everything would be easy, because then 2 to the f of k, you can essentially search and find an algorithm to find the solution for the original graph. And as I mentioned, actually fixed parameter tractable and kernelization are equivalent. This is the one that we discussed in the other class, algorithmic lower bounds. The videos are available at YouTube as well. Good. So that's about these things. Now, so we talk about this simple algorithm. So vertex cover. What was the problem again? That you want to find a set of vertices S. So every edge has at least one vertex in S. And in the simple case that in the stream you are just inserting the edges, and this was the idea that you are maintaining a matching M greedily on the graph so far. So what's the meaning of that? It means that if an edge is coming and both of the endpoints, and everything is order n, both of the endpoints are not there, then you will insert it to this matching. And however, if there is an edge and one of these things essentially, if for any v in the matching. Yeah. So and the idea that for any edges in this matching, we also keep up to k incident vertices. So if there's one edge that is coming and it is incident to one of these match vertices, if that vertex has at most k vertices so far, we will keep that vertex there. And so this was a order k to the two essentially. So the space here that we need to do it is order k to the 2. Why? Because so here that was the idea that here the size of the matching can be at most k. This is the matching part. So it is at so this matching can be at most k. Why? Because each edge of this matching needs at least one vertex cover. So if the vertex cover is k, so in that sense, promise streaming, parameterized streaming is some kind of promise streaming as well. Because it is promise that the solution would be k essentially, and you want to do it something based on k. There are some other versions that you don't know k, and based on any k, you just want to have the guarantee that the space should be at most k. But these are different variations. But here, let's say we know k essentially. Then the size of the matching cannot be more than k. And each of these vertices, you can essentially the degree of each vertices cannot be more than k. Why? Because if there are more than k vertices, then we know that. So if there are more than k adjacent vertices for a vertex, it means that this vertex for sure should be in the vertex cover. Why? Because if this vertex is not there, then you need to cover all of this, and that would be k plus 1. So in that case, we know that this vertex should be in the vertex cover, so we can delete this vertex from the and all adjacent edges, and then continue. So the total size would be essentially the size of the matching, which is 2k vertices. Each of them, the degree of them is at most k, and it is 2k to the 2. And this is actually the best that we can do it in terms of number of edges. So there is a tight lower bound that in the streaming model, you cannot do anything better. But that's the thing that we discussed previous time. The catch there. Good. Good. But what was the issue here? This was the problem of it. The issue that this works for the insertion model and everything is fine. That was the original algorithm that we had it. But the issue that what about in the dynamic case? The dynamic case is that the edges can be inserted or deleted, or like these are like friend and different or unfriend in Facebook or nowadays on everything essentially. Why the main issue is that about these matching edges? We had these matching edges, and the issue is that these matching edges, if some of this, the whole proof was based on the fact that all we have a maximal matching, and we will keep a maximal matching. The problem is that this maximal matching things may break down if you delete one of these edges. Because if you delete one of these edges, then you need to find another maximal edge, another maximum matching. And the issue is that maybe some of these vertices that some of these edges that you already forgot, you didn't keep them, you need them essentially to make it into the graph to make essentially maximal matching. Or even if you want to keep one of these edges which are adjacent, then in that case, you may need to keep essentially k vertices for this vertex as well. And that's essentially the one that makes it complicated. So this algorithm does not work. The current algorithm does not work essentially for the maximal matching case essentially. When we have both insertion and deletion. So we could actually solve this one, this promise version, so we could, but the issue that now when you do insertion and deletion, what is the size of the matching at all time? If it is promised that the size of this vertex cover essentially is at most k all time, then this is the paper that we had it essentially and in SODA 2015, and this is the SPA paper that we could actually solve this one. It is simplified version. I will talk about it here. However, removing that promise was very important thing. So that what is the idea? And it was a non-trivial problem, as I mentioned previous time, that here essentially you are starting maybe with empty graph. At some point you have a complete graph, then you will delete it, then you will have an almost complete graph, and so on. At the end of the day, you have a graph that has k vertex, vertex cover of size k. But not in the middle. In the middle, the size of the vertex cover can be as large as n. Can you, in this case, essentially guarantee that you are finding essentially this, essentially like this fixed parameter streaming, or even like 2K approximation for vertex cover in the final graph? So that was a thing that was quite non-trivial, and it is exactly because of this reason, because you are inserting and deleting lots of edges. I will talk about this algorithm briefly as. But first, we are talking about, so this is essentially, this is no promise case. And this one is the promise case. And this is the simplify. So I want to talk about this. So here, I especially need two data structures. These are actually very nice structures, which are used a lot when you are using this kind of a streaming algorithm, and they are very useful. So what are these? So it is the first one is so one is k sparse recovery, and the other one is k sampler actually. What is a k sparse recovery? It's a data structure which accepts insertion and deletion of n elements. At any moment, if the current number of elements stored is at most k, then all of this can be recovered in full. Good. So this is the idea that, I mean, this is the data structure. You can insert and delete the things. And at any point, I mean, the number of edges, at some point, you may actually add it more than k. We don't have any guarantee there. But if you know that at any time, the number of stored is at most k, then I can recover all of those k correctly. There's a deterministic construction for that, which requires k polylog n space. Second algorithm, which is essentially based on the previous algorithm, essentially, or it is via k space sparse recovery. Essentially, so that when it is sparse, I should be able to get them correctly. Of course, this correctly is important. Those that are remaining, I should be able to get it back. The k sampler is very similar to that. It's a little bit, I mean, it's essentially handling the case that this k sparse recovery cannot handle. It said that if I want to get a data structure which accepts insertion and deletion of n elements, at any moment, it can provide a sample of size k from the elements stored in it, provided there are at least k elements in it. Good. So he said that now here, that was exactly the part that k sparse recovery didn't have any essentially guarantees. Here it says that if the size of this element is greater than k, then I can have essentially a sample of k elements from this. I mean, it might be, I don't know, n or much larger than k. But at that time, I should be able to provide, say, essentially uniform sample of k elements from this h elements that I have in the sparse, essentially this k sampler. So together, what is the whole thing that this, and this actually the proof of this is there's a randomized algorithm, and the space is k polylog n. This is the one that, so it is essentially, we will call it somehow, in this case, O tilde k. So this is the idea that using these two algorithms, what can we do? If the number of elements is less than k, then you can get from the k recovery essentially all k of them. If it is greater than k, then you can get a k of them, essentially sample k of them, essentially say uniformly at random from all the elements there. So that's the whole idea that we have it in these two algorithms, and they are actually using very nicely together. Now, let's see how can we use that one for the problem that we had it. This was actually a non-trivial thing for even the insertion and deletion. It was a non-trivial thing. So here our data structure has two parts. So we try to use essentially mimic this algorithm of matching algorithms, but when we will keep the matching and k adjacent vertices to every vertex in the matching. So here our data structure, has two parts. A set of k sampler, a set of k sparse recovery as well as k samplers. Essentially for the part to keep the sorry. So here essentially we have this matching. So here this matching L we will talk about the set L. Now for each of these vertices, instead of just keeping k vertices, I try to keep essentially k sparse recovery for them. But it is actually this is the combined structure: k sampler and k sparse recovery. So essentially, when these neighbors are coming, it's natural to actually use this one. It was not easy, the first algorithm, but this is the way that actually you can do it. So for each neighbor, I will essentially keep the combined k-sampler and k-sparse recovery. Okay. Now let's go to the algorithm. And then L would be this kind of, essentially it would be some version of it. These are the edges that induced by vertices degree less than k. So this is essentially a generalized version of the matching. So let's see what is the exact algorithm actually. Good. Okay. So let's talk about insertion of the edges. What is that? So when we are inserting any edges, uh, let's say there's an edge that are coming. If both endpoints have degree less than k, so what do? You will add the edge to the set of edges L essentially. So if this edge that you are adding essentially both endpoints have less than k degree, then you just add it to L. That is fine. Now, so that's about this case. Now, what about if you are inserting and one of these endpoints has degree k? So after the insertion, you know that one of these endpoints has degree k. In this case, so and before it was like here in this case for like when you insert it essentially this edge as I mentioned has one of the endpoints, so they were both endpoints were less than k, but now one becomes k essentially. In this case, for that vertex, for that endpoint that has degree k, you will initiate an empty k sparse recovery as well as k sampler. Then you will move all the neighbors of this vertex from L to this k sparse recovery or k sampler. And you will put a time stamp on this k sparse recovery. So when essentially such a vertex appears, you will consider this vertex before all the, so this is the one vertex that you try to, this one, so you are inserting this one. Now the degree of this becomes k. Then all these edges so far, they have been an L. You will just remove all of them from L, and then you will create a sparse recovery which has k edges there. And these k edges essentially will be inserted. And you will also put a time stamp, which one essentially. This is important for the deletion part. You will say that at what time I have created. This is like the time stamp essentially is the number of edges, number of operations that came here essentially. Good. Now let's go and talk for the next case. So the only remaining case is that when you insert any edge, then one endpoint has already a k-sparse recovery. So if one of these endpoints has a k-sparse recovery, then in this case, you don't add this edge to L or anything. You just add this edge to this k-sparse recovery. And if both endpoints have k-sparse recoveries, then you will insert it to both of them. Sorry, you don't insert to both of them. That is important. You will insert so you will add to the one that has a smaller time stamp. Good. So these are all cases. If this edge is coming, none of these 2 points essentially have any, they are essentially, both the endpoints have degree less than k in L, then you will just add it in L. In case one of them becomes degree equal to L, then you will just remove all those edges and then you will add it to a k-sparse recovery. If you are adding this edge and one or both of these endpoints have already a sparse recovery, then if there's only one, just insert it on that. If both of them have a k-sparse recovery, insert it on the one that has a smaller time stamp. So this is actually a simpler algorithm. And this was not the original algorithm that we had. This was a simplified algorithm that I have mentioned. It's a very clean and nice algorithm. Now, what about the deletion? So the deletion, if the edge that you want to delete, it is already present in L, then just delete this edge from L. And that's it. So L is some kind of residual set of edges, those edges that we have not handled yet, essentially. And then all other would be essentially stored in this kind of several k-sparse recovery that we have. Now, if this edge is in one of these k-sparse recoveries, so if this edge is not in L, it means that it should be in one of these k-sparse recovery. Then you know that, and we have this promise that you have deleted an edge which is essentially already inserted. So you will, if this is, if one of these endpoints has a k-sparse recovery, so we know that, I mean, this edge is essentially has 2 endpoints and one of them has a k-sparse recovery in this case. Then you will just delete the edge from this k-sparse recovery if it is only in one k-sparse recovery. However, if both endpoints have k-sparse recovery, then you will delete it from the one that has a smaller time. So in some sense, we put the insertion such that the deletion can be done in a natural way. If it is in L, you just delete it. If it has a k-sparse recovery, then you will go there and then you will essentially delete it from there. Good. That's the whole algorithm that now it can essentially handle insertion and deletions. Now, what can we essentially get in terms of and also one last case. If you delete an edge, and then so if the essentially if you delete an edge, and from this sparse recovery, then this have after the deletion, this k sparse recovery has less than k edges. In that case, we are using the property of a sparse recovery, so that if there are less than k edges, I can produce all of these k edges for you. What do? I will consider all these k edges and I will add it to L, and I will remove this sparse recovery. So that's this is the part that we are using a sparse recovery, that when the size becomes less than k, then I will get all these edges because of the condition of the sparse recovery. I can get them all correctly, and then I will just insert it to the L and I will remove this from the sparse recovery. Good. Now, what is the essentially the proof outline? So this algorithm actually is yeah. So what is the idea? So the idea that this kind of k-sparse recoveries, these vertices that they are in the sparse recovery, we know that they should be in the vertex cover. Why? Because the current degree of these vertices is greater than, or at least k. And we know that this vertex should be essentially, or you can say greater than k if you want to be safe side. Then you know that the size of the adjacent vertices currently to this vertex is greater than k. Because of that, we know that this vertex should be in the vertex cover, because as I mentioned, if this vertex is not there, then there should be more than k vertices in the vertex cover. So these are the information that we know that. And this is essentially the idea of this kernel. And at any time, if I want to see who are these edges and I want to create the kernel, I can use now this kind of k-sampler. So at any time, if I want to see what is the graph, this is essentially the same graph that we had it just for insertion. I can just consider the edges in L, and all sparse recoveries, I know these vertices are essentially should be in the vertex cover. From all of them, I can get at least k edges which are needed. And as we discussed before, for the kernelization, you really don't need to know more than k adjacent vertices here, because you know that this vertex should be in the vertex cover. And as I mentioned, everything which is everything either stored in L or it is stored in these k samplers. So essentially, L union P is the set of edges essentially that are in all these k samplers, is enough to create a kernel G prime to find a vertex cover at any time. So that's essentially the idea. Either we have it in L or it is stored there. At any time, this is the main use of essentially k samplers. At any time, when we want to create essentially our vertex cover or find an approximation, then we can just use these k samplers to get k samples of these edges adjacent to this vertex and create our kernel. So that's essentially the thing why it is enough. Now, what about the space thing? The space actually is not that hard. So here, the total space that we needed essentially is order. So this is k to the 2 polylog space for k sparse recovery or k samplers. Why? Because each k sampler corresponds to a vertex in a vertex cover. The size of the vertex cover is at most k. The number of k sparse recoveries would be thus at most k. And for each of them, we needed k polylog k, as I mentioned before. So k vertex, k essentially vertex k sparse recoveries or k samplers, size of them is that would be k polylog, so it would be k to the 2 polylog. Also, we have at most order k to the 2 edges in L, because each vertex in this L should cover at most k edges. Otherwise, it would be essentially in the k samplers, it would be corresponding to k samplers. And also, we know essentially this vertex should be part of the vertex cover. That's the thing that we have. So we know that each vertex in L also should have. So we can have at most essentially like they mentioned, each vertex in the vertex cover covers at most k of these edges, and we have we know that here the size of the vertex cover is at most k, so k times k would be k to the 2, that would be the size of L. So in total we have k to the 2 times polylog n space for this implementation, which is essentially order O tilde k to the 2. And this is very simple to implement. I will talk about it. But what about, I just want to give some ideas about this other approach, the second one, that when we remove this promise, what was the promise? That at any time the size of this vertex cover should be at most k. We really remove this. This algorithm that actually, and as I mentioned, it was almost quite non-trivial that in that case, actually, we can create something. This paper that we had it now, it's the base of lots of other papers that they are using these ideas. And I think that's very important to know about it. So what do we do here? Let k be the size of the vertex cover at the end. Good. So here we don't have this promise. Before k was the max size at all times, but here is just the size at the end. Here we are doing a more sophisticated approach called vertex sampling. So what do? We will hash each vertex to a number from 1 to k. So each vertex, there are n vertices, it will be hashed into 1 to k. Essentially, we color it with either 1, 1, 2, 3 to k, and will be hashed. So essentially, this is the graph that you can, then if you consider the whole graph, it would be something like this, the one that we are drawing here. But this is the whole graph. Each vertex essentially has some color from this hashing in 1 to k. Now, what do we do here? So for each pair of numbers, for each of these numbers between 1 to k. So for each pair, essentially I can be between 1 to k and j can be between 1 to k. So I have k to the 2 pairs. I maintain one edge of this data stream. So this is the thing. Now that's the way that essentially I'm doing that. So I will, this n vertices, I just hash it into this one, and that will be consistent. Now, for any of these essentially pairs of things, I will keep one edge essentially of the data stream. And I will do this one, not only one time, but log k times. So these things I will do it. I will essentially, you can consider k copies of this graph. And for each of these, all of them, the hashings would be the same number. But I will use essentially k of this thing, k edges between, do it like k times of this. So here, essentially, it is for one, I will just keep one edge. Here, I will do it essentially like k of this. Then this is a non-trivial theorem that we can prove. So that let G prime be the graph containing all these stored edges. This is log k, essentially, iterations of the previous one. That between any pairs, I will keep one edge. Assuming the size of the vertex cover is k, then with high probability, G prime and G have the same set of vertex cover as well as the matching, actually. That is the matching also, we can do that. So this is the non-trivial theorem that if you do it log k of this between any pairs of this colors, I will say, you keep one edge and you repeat this one like k times, then with high probability, actually, the size of the vertex cover and the vertex cover itself would be the same, as well as the size of the matching. So now, what is the current space that we needed? So we have essentially, how can we keep essentially between any of these two pairs? So here, how do we keep it? Essentially, between any two of these people, I will keep essentially a k vertex. I will keep a k vertex, k sparsely covered. So between any of these two Y's, I will essentially keep k sparsely covered, and that would be enough for me to actually keep one edge between any of these pairs of labels. So then, in that case, the space that I have it. So the total space that I have it would be k to the 2, because the k to the 2 pairs times like k times k like k, because of this sparse recovery, that would be essentially k to the 3. However, you can show that you can improve this one from k to the 3 to the k to the 2. And this is actually more general. So you can actually show that this result applies for any problem which is closed under vertex contraction. Vertex contraction essentially means contraction, the same thing that we discussed before. So if a property is closed under contraction, if the graph has this property, if you contract this edge and the graph has this property, this theorem, this approach works. And you can use essentially, this includes lots of things like matching, eating set cover, k-colorable graphs, and several other problems. So that's essentially the way that you can get it. And this approach that essentially, instead of just keeping these edges or vertices, hash them into k, and just for each pairs of these labels, keep one essentially edge at any time. Just make sure that you have it. And that is the reason that we can use it essentially k samplers here. That's this approach that it was quite non-trivial, actually works well. And finally, I wanted to mention something about the implementation. So these are like the dark side. You may see that because I have actually implemented this one for this big data. So these are like actually a few big data graphs. This is the World Wide Web graph and the brain graphs. And these are the size of them essentially. The raw data is 1.3 terabytes. The refined data, if you, clean it and essentially do it, still this is 200 gigabytes. So these are very huge things. And I needed to actually do this one for some, government project that I had it essentially. So this is the thing, it is so big. If you want to just do a DFS and BFS, it would be essentially almost impossible that you can do it. To just find whether one edge is there, essentially it takes 25 minutes. And if you want to just sort these edges essentially, or sort data, it takes 1 hour 40 minutes. So these are so big essentially. But how did and these are the size. So this is the graph. So this is these are the web graph, which has this essentially 101 millions of edges, and this more than 2 billions of edges. And these are some brain graph. The brain graph are essentially, these are some of the things that they create from the essentially the neural nets of the brain of the people after MRIs. I mentioned briefly before. So this is for 2 people. I have done it. I think this other person was is a bit more advanced maybe than the other one. The size of the graph was larger, essentially, like almost 2x if not. And these are some of the running time that I have. I mean, we got it. So I just use essentially I had my laptop, same laptop I'm using actually, and then I had some external hard drive that I just use that external hard drive essentially to uh, the external hard drive. I used it essentially to uh, run this algorithm there. And using this, just reading essentially from the external hard drive. And this is the time that it took for me to find this matching size and the vertex cover in these big graphs. This is like 2 hours, 3 hours, and 7 hours for different things. So I have used this algorithm, implemented them, and actually they work quite well in practice because these are like sampling algorithms. And this was the whole idea, that I have this hard drive, I just reading that one time through all the edges and can compute these things. Good. And so if you want to know more about this kind of big data, we have also provided this big D&D things. This is a project that I have done it with Eric Demain. And this is, I mean, this is something that all the graphs that we had it, or all the resources for big graph and dynamic graph, we have put it there. So if you want to implement something, you can just go there and essentially implement your algorithm based on that. So that would be great essentially to, I mean, look at it if you want to do implementation. And implementations are important because lots of these cases, essentially, as I mentioned, it was some government use that I have used my laptop, and it was a practical thing that I get it, but you might be able to do it essentially for other problems as well, essentially. So good. I thought these are some of these things actually looking forward. These are like, can we implement? So the idea that, I mean, these are like, can we implement some of these algorithms I have mentioned in the map reduce setting as well? I mean, some you can, some you cannot do that. And generally, the whole idea that we talk about is kind of vertex sampling, or this algorithm that we have mentioned for this parameterized setting. These are very set of algorithms which are called meta algorithms. These are very general set of algorithms. Can we essentially design more this kind of algorithmic framework, especially for big data, either streaming or map reduce? That's essentially a very big and challenging open problem that would be very interesting, because it gives us very general ideas about it, about the framework. And that's it. So I stop here.